Welcome to Gravity Assist, Cosmic Slingshots, where we explore how spacecraft use planetary momentum to gain speed and extend range. In this presentation, we'll cover strategic velocity gains, fuel reduction, and mission efficiency, plus the analytical tools used to model trajectories and optimize flybys, so you get a clear sense of why gravity assists are essential for deep space missions. This slide compares two frames of reference to explain how a gravity assist actually changes a spacecraft's path. From the planet-centered view, the craft's speed stays the same, but its direction shifts. While in the heliocentric system, that directional change becomes a net gain or loss in solar orbital velocity, meaning the planet's motion transfers momentum and alters the spacecraft's heliocentric speed. Here we focus on the core physical principles behind gravity assists, conservation laws, and deliberate delta-v tuning. The total energy and angular momentum of the planet's spacecraft system are conserved, but by choosing specific flyby geometry and altitude, engineers can tune the spacecraft's effective delta-v, trading turning angle, and closest approach for precise speed and direction changes needed for mission goals. This diagram shows how approach geometry controls acceleration, deceleration, and bending of the trajectory. Approaching from behind the planet adds heliocentric speed, while approaching from ahead subtracts it, enabling capture or inner orbit insertion. The amount of bending is set by hyperbolic excess speed and closest approach radius, so mission planners adjust those parameters to produce the desired trajectory change. Successful gravity assist missions depend on careful timing, modeling, and trade-offs. Synodic alignment and narrow launch windows dictate when assists are possible. Trajectory design uses patched conics and iterative targeting to refine paths, and mission planners must balance time of flight, radiation exposure, and thermal limits to achieve objectives while protecting crew or instruments. Flyby altitude is a classic risk versus reward decision. A lower altitude increases turning angle and delta-v, but also raises atmospheric drag, thermal loads, and mission risk, while a higher altitude reduces drag and heat but yields smaller gains. Determining the minimum safe altitude therefore requires accurate tracking, spacecraft tolerance assessments, and consideration of science opportunities like remote sensing. The Voyager 2 sequence illustrates a grand tour using 4 planetary encounters to reach escape velocity and maximize scientific return. By chaining gravity assists at Jupiter, Saturn, Uranus, and Neptune, the spacecraft gained successive boosts that increased heliocentric speed and reduced cruise time, demonstrating how well-timed planetary flybys can turn limited propellant into an interplanetary reconnaissance capability. This comparison highlights two different uses of gravity assists. Cassini leveraged multiple assists to build velocity and reach Saturn with heavy payload, while Galileo used assists principally to slow and shape its approach for Jovian orbit capture, including a critical Io flyby to dissipate energy. Together, these missions show how assists can be tailored for acceleration or deceleration, depending on mission needs. The New Horizons case study shows how a 2007 Jupiter flyby provided a strategic velocity boost, raising escape speed from about 16 to roughly 23 kilometers per second, and shaving years off the Pluto transit. Beyond the speed gain, the Jovian encounter also served as an operational rehearsal for navigation, instrument calibration, and systems checks ahead of the Pluto encounter. Upcoming mission architectures are combining resonant assists, solar electric propulsion, and three-body dynamics to expand возможности. Multiple flybys of Earth, Venus, and Mars plus SEP allow reach to high-energy orbits and efficient long-duration missions, while ballistic captures and multi-body exploits can drastically reduce insertion delta-v and enable smaller, more cost-effective launch systems. Looking further ahead, relativistic gravity assists conceptually use compact objects, or stellar flybys, to reach interstellar velocities. The idea promises velocity gains of hundreds of kilometers per second, but faces severe operational challenges, notably extreme precision navigation in steep gravity gradients and intense radiation environments, meaning modest, closest approaches and robust shielding would be required. In summary, Gravity assists leverage planetary momentum to produce meaningful mission benefits. Large fuel savings, extended range, and flexible trajectory shaping. The core mechanics are straightforward yet demand precise navigation and timing. And while technical requirements are strict, proven missions like Voyager, Cassini, and New Horizons validate this powerful technique for strategic space exploration.